Hello and welcome to another language design video. My name is Robin Hansen. I'm the lead developer of Gren, and today we're going to be talking about parametric modules. Now, before talking about exactly what parametric modules is, I'm going to start talking about the problem that it solves. Now, if you already sort of know this, you can skip this section, but I like to talk about language design in terms of the problem it solves. Now, in Gren, we currently have two ways of talking about types. We can either um, talk about concrete types that we know everything about, or we can talk about generic types, which we know nothing about, right? We can move them around, we can pass them into the functions, but we can't actually do anything with them because we don't know what they are. Now, every once in a while, it would be useful to do something with a type that we don't really know what is, right? So an example of that would be um, like sorting an array. We don't really know or need to know what the types are as long as we know how to sort them, right? Uh, and that functionality in other languages is known as ad hoc polymorphism. Uh, and many languages have this. In fact, most languages have this, right? Java has interfaces, Haskell has type classes, and Swift has protocols. And while these methods have differences, they fundamentally work the same way. So first, you define a contract, a function or series of functions that works on a limited set of types, right? Then you define how a type implements that contract. And then when you call a function, um, the actual implementation that is being used depends on the type itself and it's decided dynamically either at runtime or through static analysis. And this is sort of like the general approach to solve this, right? You have a contract, you have a type, and then you define how the functions in the contract behave when passed a specific type to be determined later, right? Now, Elm, which I have to mention because Gren started as a fork of Elm, and so we have inherited many of Elm's language design decisions. Elm actually supports this. Elm has support for ad hoc polymorphism. However, you can't define interfaces and you can't define implementations of those interfaces. So the number of interfaces is hard coded, they can't be expanded, uh, and the implementations of those interfaces is also hard coded, can't be expanded on. I believe there are three type classes or interfaces or protocols, whatever you want to call them, in Elm. That's number, which is implemented by int and float. Um, there is comparable, which is implemented by the numbers, strings, tuples of strings, or tuples of comparables, an array of comparables, I believe. And then there is appendable, which is implemented by a list and string. But there's nothing else. You can't do anything else, right? Now, this is mainly being used in the dictionary type, or this is specifically being used by the dictionary type, but that means that you can't really expand what can be a key in a dictionary, uh, which is a huge limitation, or which is an abnormal limitation, I guess would be more correct. And so many people ask, not many, some people ask, me included, like why is it this way? Why is it so limited now when it's basically the de facto implementation in almost every other language? Now, I'm not going to claim that I know the answer 100% to this, but my impression, my recollection of this is that Elm's view on ad hoc polymorphism is that it tends to be overused in certain languages, and this is true. Or Yeah, this is true. Like, so if you look in Haskell, there's tons of interfaces. Um, it's the same in Java. I'm not entirely, but I think it's the same in Swift. Like, so if you look at other languages, almost all of them have like a sequence type or an iterator type, and then you have a bunch of functions operating on that. And what that leads to is that unless you know how everything works and how everything's put together, you are essentially dealing with abstractions upon abstractions. And that's not always the easiest code to read, and it's definitely not the easiest error messages to understand. And I think in Elm, that has a very, very high focus on readable error messages and on code that is easy to follow. The stand simply said that, yes, ad hoc polymorphism is useful, but it shouldn't really be used as much as it is. And so both the number of them and their implementation should be limited. And in some respects, Elm can get away with this because it mostly focuses on front end development, um, where you don't really need as much dynamic, or at least where it's not that common to use as much ad hoc polymorphism. Uh, but of course, that's not the only problem with ad hoc polymorphism. One problem that I find in particular is that you are essentially it's essentially a race uh, to be the first to implement. So um, if you have a compare interface and the string type implements that interface, no one else can provide a different implementation of the compare. Uh, and for strings in particular, that's actually a big limitation because sometimes you want, like, string can really be sorted correctly in many different ways depending on what the string represents. It's a very generic type. Sometimes you want to sort strings alphabetically. Sometimes you want to sort them in reverse order. Sometimes you want to separate lowercase from uppercase. Sometimes you want to do semantic versioning sorting, right? There are many ways, many valid ways of comparing something depending on context. Um, but with ad hoc polymorphism, you tend to only have one and exactly one implementation of a given interface, and there doesn't really tend to be a way to override the implementation on a case by case basis. You could create a new interface and then implement that. Um, if you have like an ad hoc polymorphism system that allows implementing an interface without actually owning the type, you could wrap the type and then implement the interface for that wrapper, which is also common. But then you have to start converting back into, uh, but either you have to convert to and from that wrapper type, or you have to implement the functions you need on top of that wrapper type, all of which are bad situations to be in my opinion. Um, and of course, finally, and this is more of like a language design thing, I find it weird, considering we're a functional language where types and functions are separate things. I find it weird with ad hoc polymorphism implementations that these are intertwined, that these are tightly coupled. Elm has some issues with it. I have some issues with it. And so I've sort of tried to find a design um, that takes all of these objections, if you will, into consideration. Um, and of course, for Gren, I think, like, I felt the need for this feature in Elm, But in Gren in particular, we have a larger scope. We want to do back-end development stuff. We want to do command line applications. And some way of supporting this becomes more important, I think. Gren is not going to take the approach of thinking that we know every situation you're going to need this sort of feature in. That wouldn't be possible because the scope is bigger. We can't do that. Um, so I think this feature is a good feature. I think we need the feature, but it would be nice if we could add it in a way that um, answers or yeah answers to all the objections or all the the cons that I just mentioned, right? And the closest thing that I found was functors in the language of Camel, and our implementation of that is what we call parametric modules. So, to explain what parametric modules are, I want to first focus on a higher order function. So, the array map function uh, changes one array or changes the values in one array, creates a new array, and then copies the valued over, modified with a function that you provide. How the modification happens depends entirely on a function that's passed in as an argument. Now you can imagine sort of that whenever you call map, the compiler will create a new version of map specialized over the function that you passed in. That's not what happens today, but the compiler is free to do that if it decides to. Um, and this means we effectively have infinite number of versions of map uh, depending on the function you pass in. Parametric modules is the same idea, but lifted up at the module level, right? So you could imagine, and by the way, the syntax here hasn't been fully decided yet. So, don't get hung up on the syntax. We'll get back to this. But imagine for a second that the dictionary module was implemented as a parametric module. You can see here that the first import is a signature. We're importing a signature module called compare, and we're calling it key. And then our definition of what a dictionary is, the key is actually defined by the key module called compare, right? And compare is a signature model. What that means is this. So this is how compare is implemented. It's a signature module as claimed. It has a type alias t and a compare function signature. So the interesting thing here is that a signature module has no implementations. It's just a list of what a module needs to have in order to be compare compliant, right? So you can imagine um, in the Dict module, when we're doing an import signature compare, what we're really doing is specifying that this module takes a parameter, which is, again, a module that looks or at least follows um, or has this shape of the things that is listed in the compare signature. You can imagine a signature module as kind of being like a type definition for a module. And when you import a signature module, what you're really doing is saying that this module takes a parameter. I hope that was clear. It's hard for me to see if I'm doing this correctly, but it's really the same thing as a higher order function. We're doing higher order parametric modules here. Now, the interesting thing about signature modules is that we're just defining a shape. No one has to implement a signature. Any module that has a type alias t and a compare function is compare. That's all there is to it. So you might implement or you might import a dictionary like this. So import dict string, and this is not the string type, this is the string module. So we're importing dict, which takes a parameter, and we pass in the string module as that parameter, which will return a dict module specialized on the string module. Right? Effectively, it will give us a dictionary where the keys are strings. Now you will see there's this extra bit of syntax here called where, and that's because the string module doesn't actually have a type alias t. So the where syntax allows us to say that, oh, and when you see t, what we're actually talking about is the string type, right? So using parametric modules, we can do like generic collections where we know a little bit about the type, where we know how to compare things. Um, now, um, if we wanted to have a dictionary with a string key, but we wanted to override how things are sorted, we could simply define a new module like this. So here we define a module, semver sorted string, that exposes a t and a compare function. So here the type alias t is string. This is a normal module. This is not a signature module, so you will see implementations here. But type alias t is string, and then the compare function takes in two strings and returns an order. I can see that my video kind of cuts the example, but I think it's easy to understand what I'm aiming at here. So with this simple implementation, we can now import dict passing semver sorted string as the parameter, and this returns a dict where the key is the string, right? Same as before, but where the comparison function that's being used is a comparison function that sorts strings according to semantic versioning. Now, when you do things like import dict string and import dict semver sorted string, which are different modules, you also end up with different dict types, right? So these types are not interchangeable. And so now you have, even though in both cases you have a dict with string keys, they are still different dictionaries because they're specialized over different modules. And this means that you can't do a dict union on dictionaries that are sorted differently, right? So that gives you sort of like a compile check that these are in fact sorted according to the same comparison function. There's an additional benefit with parametric modules. Not only can you override how parts of the interface works by creating your own module, and without wrapping the type, but you can also use this as an inversion of control mechanism, where you can define a module that does a lot of things, but requires a parameter to decide like what are you going to do with that logic. And in your tests, you can essentially mock out that final bit. Like imagine that you have a module that does some computation and sends that over the network, or it sends that somewhere, right? Performs a side effect. In your application, you could have it perform the side effect through a parametric module. And in your tests, you can mock that functionality out, right? Parametric modules makes that very easy. Now, parametric modules also has some limits, right? It's not a panacea. Nothing ever is in language design. And to talk about that, let's look at like array sort. Array sort is very simple. It takes an array of comparable values. This is, how our current limited type classes work. It takes an array of comparable values and returns an array of comparable values, preferably in sorted order, right? Now, if you were to do this with parametric modules, you would have to make the entire containing module a parametric module. And you probably don't want to do that, right? You probably don't want to make your entire module parametric because you thought it would make a nice convenience function. Like a single function would be a bit better for it, right? Um, so either you would create a new module that is parametric, that sort of like gives you um, parametric, functions. Um, uh, but or perhaps more likely, we just not do that and use array sort with instead, where you pass in the sorting function. So, but this still kind of like shows that you wouldn't use parametric modules in all the same ways as you would ad hoc polymorphism, because for narrow cases, or when you just want a single function to be a little bit magical, lifting everything up to the module level becomes more trouble than it's worth. And that might seem like a big downside, and it sort of is. It's a big limitation, right? But if we look back to the problem statement, one of the reasons why Elm has limited ad hoc polymorphism is because it tends to be overused. And this limitation, while it might be annoying, or it might actually limit the usefulness of the feature, for Gren, it might actually be the limit we want, because we don't want people to use parametrics, the polymorphism everywhere. And so the fact that parametric models are a little bit limited by the fact that they are, a module level feature, might actually work in our favor, because we don't really want to introduce a feature um, that makes the language feel off. Like, so we have a lot of modules that implements map, fold, filter, right? And those are not defined using polymorphism. In other languages, they tend to be defined with polymorphism, ad hoc polymorphism. In Elm and Gren, they are not, and that's not due to the limits of the language. That is intentional, right? And so parametric modules fits better with how the language works today. Um, and it might also prevent people from over abstracting things. Right? So with those things out of the way, the big question is, when is it ready? So we hope to have parametric modules available in 25W, or the 2025 winter release in December. Uh, and another goal of that release is to rewrite the parser and reintroduce a code formatting, which means that I hope to implement this as I'm rewriting the parser. Now, the plan is to do this in a backwards compatible way. So we're likely to keep our current limited type class functionality while we implement, or while we evaluate parametric modules, um, which gives us a nice way to backtrack if we find out that this is a horrible feature. But it also makes it easier for people to migrate as we do this. And of course, the implementation is likely to start off very, very naive, but will be gradually refined as we work on this. So it will be ready by the end of the year is the plan. Now, some of you might be thinking, currently we have a bunch of math operators that work on numbers, which use type classes. In a fully parametric module world, is that going to change? Since Gren is aiming to be like a small minimalist language, where we're unlikely to retain both ad hoc polymorphism and parametric modules, one of them is going to win. And if parametric modules win, what's that going to do to operators? Now that is the subject of the next language design video. Operators, custom operators, how is it going to work? And I hope to publish that at around the same time next month. So stay tuned for that. In the meantime, thank you for watching. Please, if you have any questions, consider joining our Discord channel to talk about it there. We have a language design channel made for stuff like this. Or, leave a comment in the comment section below. Right, that's it. Thank you for watching, and I'll see you in the next one.